Welcome to problem number 5 from the 1.5 topic questions. There's the problem. I broke the picture up into 2 steps. Please note that I've added some extra labels for myself. I've noted that just before it hits the wall, it's going V1, and I carefully drew it, tried to make sure that I thought of it as horizontal. When it rebounds a negligible amount of time later, it's traveling half of that speed, but also just horizontal. So it might be worth noting that V1, the y component of V1 is 0. So V1, y component is 0 in both cases. In both cases, right? And that's important to note because the motion, right, it's not being thrown down, okay, it's just leaving at a 0. Here it's leaving at a 0 vertical velocity. It's leaving at half V1 horizontal velocity. Over here, it's going up with initial x and initial y, V0 as at an angle, but by the time it gets up here, its velocity is 0. And they want us to find the amount of time it takes in terms of V0, theta, and g to go from here to here. So just to help me out, I'm going to go this first upward journey I'm going to call A, and this downward journey I'm going to call B. Quick visit through the projectile motion model. These are the same kinematic equations we've had all this time. The only difference is that we include the special case of projectile motion, which means that in the x direction horizontally, there's no acceleration. So these equations simplify. Really, there's only one real equation. It's this one, which is the t squared equation, but with no acceleration. It's really constant velocity. These are just constant velocity equations. The final velocity in the x direction after a certain amount of time t is the same as its initial. It just depends on how far it's gone in the horizontal direction divided by how long it took to do that. The y direction is where all the action's at. Okay, you've got acceleration always downward, so you've got these equations rewritten to take into account an acceleration that's downward, negative, if up is positive. Up doesn't have to be positive, it's just a typical starting point or typical choice. And instead of acceleration, I've got g. Okay, what are some other things about the upward motion? We know that at the peak, the velocity in the y direction is 0. Okay? All right. So let's try and figure this out. If I've got A and B, something's going up and now it's coming back down. In both cases, so in A, I've got my final velocity in the y direction is 0. And over here in B, I have my initial vertical velocity. So Vy0 is 0. Well, hold on. So if I travel a certain distance to go up until my velocity is 0, right? The amount of time it takes to travel anywhere only depends on my motion in the y direction. In A, if I end up at 0 and I start, Vy initial is just what? V0, the y component of that velocity. So the amount of time it takes to go from there to there, what's my acceleration? G downwards. Okay, so I could relate this by just going, all right, I'll look at this middle one's probably the easiest. Vy is going to equal Vy0 minus gt. So the time it takes me to do that is just going to be, well, let's do the substitutions carefully or lay them all out. In the journey for A, that's 0. I started at V0 sine theta, and I slow down at g for a certain amount of time. So how long does it take me to do that? Well, the amount of time is just v naught sine theta over g. Okay, well, for part B, what's happening? I have a velocity, but it's only in the x direction. My initial velocity in the y direction is still 0. So it's as if I'm just dropping the ball. In other words, the time it takes for this ball to do that is the same amount of time it takes the ball to just fall, right? At g. So I'm accelerating g downward. Over here, I'm slowing down g downward, right? I mean, this is a -2. But I must have some final velocity vy. Well, wait a minute. If I'm traversing in the same amount of space, since my change in vertical space is the same between A and B, and I'm really, the acceleration is g, then the time it takes for me to go up and hit 0 velocity is the same amount of time it takes for me to go down and hit 0 velocity, right? I'm just going to say TA. I'll label this now as A. That time is just going to be equal to TB. What's TB? Or if you just need an equation, well, I could use this equation because it just talks vertical velocities. And I could say that if I'm starting at 0, my final velocity Vy is equal to Vy naught t minus gt. In the b direction, I've got Vy at b, right? And this is all b, but this is 0. So I'm just falling. So that's got to be minus gt. So however long it takes me to do that, I'm just falling. Another way to think of this, so this is the answer. Another way to convince yourself of that is to just draw the velocity of this thing, for any projectile actually, in the y direction. Just the velocity in the y direction. I'm launched at Vy naught. And I slow down to 0. My velocity shrinks to 0, vertical velocity shrinks to 0 up here. The slope of that thing is minus g. Now, if I come back down, maybe the main takeaway is this is a trick. It's a distraction. That velocity that I have coming back in the x direction doesn't matter as long as it's horizontal, because I'm leaving at the same vertical velocity that I had right here, which is 0. So when it hits the wall, it's really right here where it hit the wall. There's a time. And I'm going to accelerate minus g. So the slope of this graph is the same. Well, didn't I fall the same amount? If I fall the same amount, then this area has to be the same as this area. The only way those two areas the only way they're going to be the same is if the base is the same. Right? The base of the triangles. So another way to put it is, if you look graphically, there's an algebraic way to do this, but the graph does wonders, right, for you. Since delta y in A is equal to the change in height on B, delta change in vertical position, or vertical displacement, since those magnitudes are the same, and it's the same line, right? Same line. That has to force, that forces TA to equal to TB. So if TA equals TB, then how long does it really take me to go from launch all the way up, boom, and come back down? Home free, right? But the total time T is just going to be 2 times the amount of time it took me to go up, which is this guy. 2 V naught sine theta over G. Right? And this is why that answer is the answer. And that is number 5.